Okay, this concept of periodicity in frequency for discrete time signals leads us to explore something known as aliasing. So what we want to examine here is, is it possible that the sampling of different continuous time sinusoids leads to identical discrete time sinusoids? So let's first consider x1 of t, a continuous time sinusoid that has a frequency of 200 hertz, and I'm going to sample at t equal to n times capital T, where t is 0.001 seconds or 1 millisecond. Okay. And then so the corresponding x1 of n sequence is, I make this substitution for t is equal to nt, where t is 0.001, and so I'll get 2 pi 200 times n times 0.001, or cosine of 0.4 pi n. Okay. And this maps directly to a sinusoid with frequency in interval from 0 to pi. So the apparent frequency of this sequence is 0.4 pi. Now let's take a look at sampling a second signal, x2 of t, cosine of 2 pi 1200 t. And if I looked at both these signals on an oscilloscope in the continuous time domain, it would be apparent. It would be easy to distinguish between the signal at a frequency of 200 hertz and the higher frequency signal at 1200 hertz. But I'm going to sample this sinusoid also at the same also with the same rate, also at 1 millisecond. Let's see what happens. So x2 of n would be cosine of 2 pi 1200 n times 0.001. So this would actually become cosine of 2.4 pi n. This is identical to cosine of 0.4 pi n. Okay. So here I've got a case where I've got two continuous time signals that are obviously different in the continuous time domain, but if I sample them after sampling, they're indistinguishable. The sequences are indistinguishable. There's a theorem called the sampling theorem. I'll write out here. To avoid this problem of sampling and getting indistinguishable sequences, we must sample at a rate at least twice the highest frequency. So in the previous problem, I had F1 was 200 hertz, F2 was 1200 hertz, forget one bit. Doing a video. I'll get it later. And according to the sampling theorem, I need to sample at a frequency now of twice the highest frequency. In this case, that's f2. So I need to sample at twice that is 2400 hertz. And so the corresponding sampling time is 1 over that frequency, 1 over 2400, or 0.417 milliseconds. If you recall, I was sampling at 1 millisecond. This is less than that, so I was undersampling before, and so x2 of t was aliased to an omega equal to 0.4 pi. So all frequencies actually above, in that case with the sampling time of 1 millisecond, the sampling frequency would be 1000 hertz. So and half that would be 500 hertz. So all signals, all continuous time signals with a frequency above 500 hertz would be aliased into that range from 0 to pi. So now if we look at sampling at this rate, so for sampling omega 1, the corresponding frequency would be 2 pi 200 times t, or that evaluating that turns out to be 0.17 pi, again with this value of t. For omega 2, it's 2 pi times 1200 times t. That corresponding frequency is pi. So now these two discrete time signals would have different apparent frequencies, so we'd be able to distinguish between them. So this is a very important result, especially as we move into sampling of continuous time signals, that you have to keep in mind that in order to avoid aliasing, I need to sample at a rate at least twice the highest frequency I'm interested in sampling.